Let's look at 2010 AP Physics B FRQ question together. So in this question, we have the plastic card shown in the figure above has a mass of 2.5 kilogram and is moving with negligible friction on a horizontal surface. Attached to the card is a rigid rectangular loop of wire that is 0.1 meter by 0.2 meter and has resistance of 4 ohm and has a mass that is negligible compared to the mass of the card. The plane of the rectangular loop is parallel to the plane of the page. An uniform magnetic field of 2 Tesla perpendicular to and directed into the plane of the page starts at x equals to 0 as shown above or in our picture. On the figure below, indicate the direction of the induced current in the loop when its front edge is at x equals to 0.12 meters and justify your answer. So as loop enters magnetic field, the magnetic field inside of the loop is going to increase and the current induced by the magnetic field is going to be opposing that change. So the magnetic field inside of the loop is going to be, instead of going into the page, is going to be coming out of the page and going into the page outside of the loop. So this way it will oppose whatever is happening to the magnetic field, to the loop. And so the current has to be in the counterclockwise direction. For B part, they say when the front edge of the rectangular loop is at x equals to 0.12 meters, its speed is 3 meters per second. Calculate the following for that instant. And they ask you to calculate the magnitude of the induced current in the rectangular loop of the wire and then the magnitude of the net force acting on the loop. So for B, to calculate the current, I need to know the EMF. So the current is going to be equal to the EMF divided by the radius, where EMF is equal to the negative n, a number of the loops, and there's only one. And then I can skip the negative because it just tells you that the current or the magnetic field created by the current opposes the change in the magnetic field of the loop. So that's going to be the change of the flux over the time, which is B. And then I have the length and the height of the loop divided by the time. The length over the height gives you velocity, so that gives me BHV. So I can calculate the current by B is given 2 Tesla, H is 0.1, velocity is 3 meters per second, and the resistance, so that was for EMF, so that was my EMF in the numerator, and the resistance is 4, so that will give me 0.15 amps. And for the second part, they ask you to find the force acting on the loop. So the magnetic field force is equal to BLI, BL and I, and sine of 90 degrees because the loop is perpendicular to the magnetic field. So I have B is 2, and instead of L, it's the height because it's not the horizontal lines, it's the vertical line that is interacting with the magnetic field line. The other two will cancel each other, the top and the bottom one. So I have H and then I, the current, and then the sine of 90 degrees. And so the B is 2, H is 0.1, and current we just found is equal to 0.15. So that gives me 0.03 newtons. And for C part, they're saying at a later time, the card and the loop are completely inside of the magnetic field. Determine the magnitude of the net force on the loop at the time and justify your answer. Because when the loop is fully in the magnetic field, the flux is not changing. So if the flux is not changing, then I have the EMF is equal to change of the flux divided over the time. So flux is not changing, flux is consistent when the loop is completely in a magnetic field. So that is equal to 0. In this case, my current is also going to be equal to 0. And because the force is equal to BHI, so the force is going to be equal to 0 because there is no current in the loop. So the net current, or the current, is equal to 0, and the force is also equal to 0. The magnetic field force is equal to 0. And that will be it for this question, and thank you for watching it, and I will see you in the next video.